This video is going to be a quick look at the first order approximation for real valued functions of n variables. This is something that you've worked with before if you've seen calculus, so I just want to tie it to our recent study of differentiation for functions from, generally speaking, Rn to Rm. Here we're looking at the specific case where the output is just a scalar. Since the function maps from n-dimensional space to one-dimensional space, the associated matrix for our first order approximation is 1 by n. It's a row whose entries consist of the partial derivatives of the output function, which is just f. So that might look like f sub x1, there we go, evaluated at p, f sub x2 evaluated at p, all the way through the nth entry, which is df dxn evaluated at p. So each of these is a partial derivative of the function with respect to the various inputs. When we looked at the Jacobian matrix, we said that these are all the same entries that you would find in the gradient vector. The gradient vector is a vector, it's a column. So here we want to think of our associated Jacobian matrix as the transpose of the gradient vector. That means when I want to write my first order approximation, typically we would write that the first order approximation centered at p, it's a function of x, and for all functions that are differentiable at p, it takes the form f at p plus df at p acting on x minus p. I'm not done yet because I want to adjust this. All right, so this is the general expression for the first order linear approximation for f centered at p. But if we are looking at the special case of having a scalar valued function, we can take this part and write it differently. Let me do that two different ways, and I'll just do it right here. The first thing we could do is say that df at p has a special form. It looks like the gradient of f at p transpose times this vector. So this is a row, this is a column, so you would just like multiply them together with your fingers and you would get a scalar output from doing this matrix product. But my favorite form for the first order approximation for a scalar value function is not to write this matrix product where it's 1 by n times n by 1, but rather recognize that the gradient is a vector. And when we do this matrix product, what we're adding up is the sum of a bunch of pairwise products coordinate by coordinate. That is the same thing as taking the dot product of the gradient at p with the vector x minus p. And this is how I most like to represent the first order approximation for a scalar valued function. The reason being that, if I just left it with dfp, what we started with, it's not wrong, but I think it overlooks the special form that our computations take when we're looking at scalar valued functions. So it kind of hides the fact that the Jacobian matrix has this very special form. And moreover, to a scalar valued function, we do things like compute gradients. So then the gradient transpose times x minus p is fine, but I really like to bring in the dot product here and say it's this vector dot that one. Okay, so let me write down two very famous first order approximations that you'll recognize because you've seen them many times, especially the first case. When we are looking at a function of one variable, y equals f of x, the first order approximation is the tangent line approximation. So I'll write, how about I center this computation at a? So if my function is differentiable at x equals a, then the first order approximation centered at a, it's a function of the scalar x, and it's going to be f at a plus the gradient of f at a dot this, but this is just a 1 by 1 matrix. So it's a scalar and it has a very special name in calculus. We call it f prime of a. So this, of course, is the preferred form. Again, if you wrote df at a for a function of one variable, which is scalar valued, it's just hiding a lot. So it's hiding the fact that everything here is a scalar. For a function of two variables, say z equals a function of x and y, the first order approximation centered at, say, AB is the tangent line approximation, or sorry, tangent plane approximation. So that would be f at AB plus, let me take this form, the gradient of f at AB dot the vector x minus a, y minus b. When I teach multivariable calculus, this is how I like to write tangent planes. But I know that in a lot of text, it's written out a little differently where this dot product is expanded. So if that's what you were expecting to see, let me tie it together with what I have here. So the first part is just f of a and b. This gradient is df dx at AB, df dy at AB. So if I actually did this dot product, that would be df dx at AB times x minus a plus df dy evaluated at AB times y minus b. Okay, so that's really all I wanted to say. I have a couple examples just setting this up and using it. But what I really wanted to call your attention to with this presentation is that for a scalar valued function of n variables, the Jacobian matrix is very special. It looks a certain way. It's a row. And there's a name that we give the coordinates in that row. We see the gradient of f. You see it in physics computations. You've worked with it in multivariable calculus. So I really like, instead of having this form, having this one, and taking that even one step further and writing what we think of typically as a matrix product as a dot product of two vectors. Okay, I'll step aside and then we'll come back and just look at some very specific examples. This is a toy exercise, but I want to practice recognizing the terms in the tangent plane approximation that we just wrote down. So for this function from R2 to R, scalar value function of two variables, assume that we know it's differentiable at the point 1, 0, and at that point the function's value is 5, the partial derivative with respect to x is 3, and the partial derivative with respect to y is 2. With just that information, let's estimate the value of the function at 3 points near 1, 0. We won't be able to say how good our approximation is, but we will just evaluate it based on the tangent plane approximation. So for this first one, we want to move from the point 1, 0 to 0.980. So only the x coordinate is changing. When I set up my tangent plane approximation, we'll say that the function's value at this new point is approximately the function's starting value of 5 plus df dx at 1, 0, that's 3, times the change in x, so that's 0.98 minus 1, and then plus df dy at 1, 0, which is 2, times the change in y, which is 0. Okay, now I have to do this number crunching in my head. So this is 0.02, so that's negative 0.02 rather, the sign here matters. So negative 0.02 times 3 is negative 0.06, so 4.94. Take a moment to do the second one and then the third one. So it's not really different than what I did here, but just make sure that you understand how to use these values in the tangent plane approximation. All right, for the approximation where we are only changing the y-coordinate, it's going to be 5 plus 3 times 0 plus 2 times 0.1. So df dx times the change in x, which in this line is 0, plus df dy times the change in y here, it's positive 0.1, so that overall this is 5.2. And then for the third line, we're changing both x and y. So we'll have 5 plus 3 times negative 0.02. Here I'm just putting the change in x, plus 2 times the change in y. So that's going to be 5.2 minus 514. Okay, that's all I wanted to run through with this example. Sometimes it's a little disappointing when you don't know what the function actually did at these points. So for our second example, I'll give you an explicit function, and we will write down a tangent plane approximation, use it to estimate the value of a function at a point near where we center our approximation, and we'll compare the two. Let's wrap up with this example. It should be quick because we've seen this kind of computation before in multivariable calculus. So we would like to linearize the scalar valued function of two variables given by f of x and y is x to the fourth plus y squared at the point 2, 1 in its domain. So we will center our tangent plane computation there. And then we will use that approximation to estimate 2.1 to the fourth plus 5.9 squared. Unlike in the previous example, I can tell you what that is so that we can see if we did a good job. Okay, so let's compute the gradient of f at 2, 6. Really, the only mistake I see when students do this kind of computation is they would put in 2.1 and 5.9 here, and that's just not right. We're centering our computation at 2, 6, and then we're going to move away from 2, 6 and use the estimation that we create to estimate our function near this point. Okay, so this is going to be a vector. I'll write it as a 2-tuple. It's 4x cubed 2y, where I want to note here that this is taking place at a specific point so that we actually have equality here. So then that's going to be 2 cubed is 8 times 4 is 32. And then 2 times 6 is 12. Okay, so that's the coordinates of the gradient. It is the gradient. That means that our tangent line approximation centered at 2, 6 is going to be the value this function takes. So that's 2 to the fourth. I'm kind of put here what I'm doing. 2 to the fourth plus 6 squared. Again, we're centering our computation at the nice numbers. So don't put 2.1 to the fourth and 5.9 squared there. Okay. Plus this vector dot this one. Again, 2 and 6. Okay. We're basically ready to go with the approximation, but I'll let you see if you can wrap it up. So see if you can estimate the function's value at 2.1 and 5.9, and then I will come back and finish the computation. To finish this exercise, we want to use our first order approximation centered at 2, 6 to estimate f of 2.1, 5.9. Okay, so again, only mistakes I see really are putting in like 0.1 and negative 0.1 here. No, we're saying near this point, estimate the value of the function at this point. So this should be close to that. All right, this is 52 plus 32 times the x coordinate minus 2. So that's 2.1 minus 2 is 0.1. And then plus 12 times the y input minus 6. That's negative 0.1. And I did just do this in a calculator. It's 54. Of course, we can also actually evaluate 2.1 to the fourth plus 5.9 squared. And when we do, we get 54 I believe 2581. So reasonably close. That's all I wanted to do in this lesson was just remind you of how the first order approximation looks when you have a scalar valued function. And very famously, you've worked with tangent lines before, you've worked with tangent planes before. I'm not going to do another example, but I want to mention that if we had a scalar valued function of 3 variables, so perhaps you have a function that at any point in your room, so a 3-dimensional domain is measuring the temperature. Your approximation would be the same idea. It would be the value your function takes where you're centering the approximation plus the gradient dot x minus the x coordinate of the center, y minus the y coordinate, and z minus the z coordinate. So it would be the exact same computation here. It's just your vectors would have 3 entries instead of 2. Okay, thank you for your attention.